We're going to talk about light waves. And when I say light waves, let's really just talk about the nature of light. Is it a wave? How would we know it's a wave? Well, ancient Greeks, old philosophers, thought light was a particle. And part of the reason for that is if I have one light source, if you have the sun, you stand out in the sun and you hold your hand like this, you can actually trace the line from the sun past your hand, straight line, and figure out where your shadow is. So it behaves like a particle in that it seems to go in a straight line. When it bounces off a mirror, it seems to go in a straight line and bounce like a pool ball would bounce off a cushion. So reflection and just light traveling, it tends to go in a straight line. We think of that like a particle. How is it not like a particle? If I shine a light this way, it doesn't fall in projectile motion. So it doesn't seem to behave in a particle that way. How does it behave like a wave? Well, there's a thing called diffraction. When waves pass a barrier, if this was a wall in the water and the waves are coming this way, the waves would actually bend a little bit around there. It wouldn't be perfectly calm on this side of the barrier. So that's one way. Light behaves the same way in that sense. Light kind of can bend around objects a little bit. Another way is interference, and this is a really compelling way. If you take a candle and light it up, and you take a hair, not my hair, but somebody with actual hair, and you hold it really close to your eye and look at the candle through there, you'll see this gleam off to the side. And that gleam is actually, if you concentrate on it, is little tiny images of the candle. And what's happening is the light is traveling around the hair, bending a little bit. It's diffracting around the hair and then interfering with itself. Much like if you have two audio speakers playing the same frequency, they'll interfere with themselves. They'll have constructive and destructive interference patterns that give you dead zones and live zones in the room. So your screen back there, your retina, has little interference patterns on it. Sorry for the bell. So that's how light is like a wave. Here's an example of that. Here's a thing called a diffraction grating. The diffraction grating kind of splits the beam so it can re-interfere on the other side. And you see when I put it in front, I get multiple images behind. Those are indications. Again, it's one light beam that gets basically split and interferes with itself, just like a wave would do. So how is light like a particle? Well, that's actually harder than figuring out ways in which light is like a wave. If you have a piece of metal and light hits that piece of metal, electrons can get released. It's called the photoelectric effect. And it turns out that the number of electrons released depends on the number of photons added. It's not every photon releases an electron, only photons of certain energy. But one photon of sufficient energy will release one electron. It's called quantized, countable. You can count the number of photons coming in. You can count the number of electrons coming out. So it clearly behaves like a particle in that sense. But it's never too far away from a wave because the energy of a light wave depends on the frequency, higher frequency. And low frequency photons won't release an electron. So it behaves like a particle, but it also has this wave nature wrapped up in that. So a photon is a particle that has a wave characteristic, a measurable wave characteristic. How do we model light in physics? Well, it depends on the application. Depending on the application, if we're talking about the atomic behavior of light, possibly we'd be talking about the photon as a particle. We'd be looking at the particle nature of the photon. If we're talking about interference, if we're talking about bending, if we're talking about reflection, we're generally talking about the wave nature of light. But it's going to be very clear in every one of the applications of light which one we're going to be talking about. So light, we know, behaves like a wave, behaves like a particle. But what kind of wave is it? Well, it turns out it's a transverse electromagnetic wave. So So it's transverse, meaning it has crests and troughs. And it's electromagnetic. And in fact, all electromagnetic waves, which I'm going to write EM waves, all electromagnetic waves travel at the speed of light. We can call them all light because it's almost an artificial distinction to talk about the light humans can see as different from the light we can't see, the electromagnetic waves we can't see. If we look at a spectrum of different types of electromagnetic waves, you end up at the low frequencies, lower energy. You have radio waves, which include radio, television, all sorts of communication frequencies. Then you have microwaves, a little higher frequency, a little higher energy. Smaller wavelength. As we get into higher frequency, we'll get smaller wavelengths. Then you get infrared, then visible light, this narrow spectrum where our eyes can detect these frequencies. Then you've got ultraviolet, and then you've got X-rays and gamma rays. And so going from radio waves up through past visible light and up to gamma rays, you go up to very, very high energy. The energy gets much higher as the frequency gets higher. But the wavelength gets smaller and smaller and smaller. So radio waves are very long, low energy. Gamma rays are very high energy, high frequency, small wavelength, because they're all dictated by V equals F lambda. And that velocity, when we talk about the speed of light, when we're talking about speed of light in air or in a vacuum, we use the symbol c, little c, speed of light in air or in a vacuum. So through space, light travels at the speed of light, c, which is 3 times 10 to the 8th meters per second. That's incredibly fast. That is so much bigger than any other velocity we see in physics. In fact, it is the cosmic speed limit. It is as fast as anything can go. Okay, you cannot travel faster than 3 times 10 to the 8th meters per second. So light in air or a vacuum, it's close to 3 times 10 to the 8th in a vacuum. It's a little slower, but it's very, very, very close. Is right around 3 times 10 to the 8th meters per second. That's what we're going to use. Speed of sound, think of speed of sound was 331 meters per second. Oh my gosh. Well, this is 10 to the 6th. This is 1,000,000 times faster than the speed of sound in air. So a phenomenal thing. And if we have that, then for any electromagnetic wave in air or a vacuum, C equals F lambda. You know the speed of light, check. So for any frequency, we can find the wavelength, and vice versa. Let's look at the electromagnetic spectrum. Radio waves had a lower frequency. Divide by a smaller number, you get a longer wavelength. Gamma rays had a really high frequency, a lot of energy. Divide by a big number, you get a smaller wavelength. So these wavelengths can be anywhere from down to 10 to the negative 10 meters, I believe, up to radio waves that can be 10 meters long. So the range of electromagnetic waves is just a phenomenal thing. So that's the electromagnetic spectrum, and that's one way we use the wave equation with our special speed. Now, one thing that's a little different, remember with sound, sound was kind of slow in air. It was faster in liquids and solids. This is the fastest anything can go. When light goes into a translucent substance like glass, plastic, water, it actually slows down a little bit. And it does another thing. It actually will bend if it comes in at an angle. That's called refraction that we'll talk about later. So this in light, in air or a vacuum, the speed is simple as c, and we use 3 times 10 to the 8th. We can, of course, we could have also used c as the velocity in this equation, delta x over t, to find how far light travels in certain amounts of time. but this one ends up being used quite a bit because it's a wave. Now, what do we mean by transverse? I mean, in one dimension, we could draw it like this, but the one distinction about this is it's not a particle wave, it's a field wave. It does not require a medium. Light can go through a vacuum. It's a field wave. And when we say electromagnetic, it's actually really complicated. I can't draw it here. Picture this being the electric field. The magnetic field would be coming out of the board and going into the board, and coming out of the board and going into the board, perpendicular. So you have a wave, if I can try to do it, you have two waves locked together that are doing this. Okay? So that has some interesting things, interesting aspects, including something called polarization that can happen with electromagnetic waves because they're transverse. So light is electromagnetic waves. Visible light is a small subset of that. Transverse field wave made of an electric field and a magnetic field vibrating. And we represent the speed of light in air of a vacuum with the symbol c, which is 3 times 10 to the 8th meters per second, allowing you to solve a whole lot of problems.